recording this. So yeah, you can look back on it later, and then all my slides are on the SharePoint, and the code I'm gonna share is also going to be on GitHub, if any of y'all are interested. So yeah, so this presentation is called Surviving in the Sea, not the C programming language. And SharePoint was kind enough to suggest this beautiful video for me to put. So that was great. Well, this is great. How do I get to the next slide? There we go. There we go. So what is C? Well, C is a programming language, and it's useful because it's very fast and memory efficient. And it gives you a lot of low-level access to the hardware. And it's used in a lot of embedded systems, which is why we use it on solar. Also, maybe easy to drown in. It has relatively high learning curve compared to some other languages. So that's what this talk is for, to sort of get you all a bit more familiar. And I'm going to be going over some examples during this talk, and you can find them all here on this GitHub, and you can also just look at them afterwards. Yeah, so the first thing we're going to look at are C has different data types. So you can have integers, you can have floating point, pointers, structures, and also some other things. Yeah, so the first data type we're going to go over is integers. It's one of the more commonly used ones, and these can be signed or unsigned. They can also have different sizes. Characters are also treated like integers, and if we look at my example code I've written here, so this is sort of like the syntax. So we can ignore up here for now, but this is if you want to import someone else's code, basically use hash include. We'll get into how that works later. Oh, yeah. Yeah, so is this better? Okay. So just some basic C syntax to help us read this file. We can have comments with these double slash here. We can also have comments with slash star and then end them with slash star. So maybe this is familiar if you've done C or Java or something like that before. And the way we declare a variable is we can put the type first. So int is for integer, and then we can also specify that it's unsigned with the unsigned keyword. We can also declare a character, which is the smallest integer you can have, and then whereas int will have usually will have a larger size. But sometimes we want to be specific about how big we want these to be. So we also have some types declared in this file, stdint.h, that give us things like unsigned int 8, int 8, and so on. So this will be like an unsigned integer that is 8 bits. Well, this will be a signed integer that's 8 bits. We can also declare, we can give them a value when we initialize them. So here this is 200, and we can put this u here if we want to specify unsigned, because by default, if you don't specify this, it's going to declare it as an integer that is signed. But that's just a little some trivia there. So we can also they can be variable. So all of these ones I've declared here, they are variable, which means we can change them. Sometimes you'll also hear the term mutable, but we can also declare them constant. So let's say this one here called D that I'm assigning to 12. Let's say I want it to be 12 forever. So I can declare it const here, and now I'm not allowed to change this value. So this can be useful if you have a value that you're using and you don't want it to change on accident. So you can specify that here. Yeah, so we've also got 32-bit types, 64-bit types, and we can see some examples here of how you might use them. So you can declare an integer here. So these ones here are all global, which means you can access them anywhere in the program. And what makes them global is they're declared outside of any function, just like on their own in the file. But here we have this inside of some curly braces. So this one here is limited in scope. So you can only reference it inside the curly braces here. Yeah, so we can see what this code does. Do I have any questions so far? Okay. So let me pull this over here. So I've got the same file here. And whenever you want to run your code, what you'll do is you compile it, which will translate your C code into something your computer knows how to run directly. What that'll look like is you'll run a command like this. So I have GCC, which is the name of my compiler. And then I've got -o integers saying I want my program to be called integers. And then I give it the .c file I wanted to translate. So I've already done that. But what we can do is now if I run this integers program, I can see some stuff gets printed out. So if we look at what's going on here, first I'm setting the variable b to 2, and then here this print statement, all it's doing is it's printing out b. So we see we get 2 first, and then here we can also do addition. So I can add a and b to get c. So now c is going to hold the sum, and it gets printed out. And then we see that, yeah, we get 200 plus 2. This gets printed out, and then we can do the same thing with f. So with f, I can get a larger number because I give it more bits. And then, yeah, I can keep doing this. I can also look and see that if I print out h, which isn't, yeah, Sid.
Can you set them in the problem so that they can give up?
With the make file, we'll do that later. So yes, so we can also see what's it called? Yeah, so if I declare h and I use it before I've given it a value, it's going to have a default value. So for a global, for an integer, the default value is going to be 0. So we see a 0 here. I've also got this one here that is declared without being used, and I print it out, and we notice that it's not 0. So the reason for that is the default value for something that's declared locally instead of globally is just going to be, it doesn't have a default value. It'll just be some random value. It's like not well defined. So you need to make sure that if you have a local that you like reference, you set it before you use it, because otherwise it could be garbage. It could be 0, but you have no guarantees. So any questions about this? And just, yeah.
You'll work it, I promise you, like, it creates variables in the area and then it reads whatever there before.
Yeah, that's exactly what it does. So it allocates some space for the variable on what's called the stack, and then whatever was there before is going to be what your variable is. Yeah. Out of curiosity, how much of this is like new to y'all and how much is like, oh, you've already seen this before? Okay, is it new to at least some of y'all? Okay. Yeah, because if I get to a point where I'm just going over stuff y'all already know, I don't have to go in as detail, but if we're getting stuff that is new, then that's good. So yeah, let's go back to my slide deck. Oh, if you want to see an example of me compiling this, the command I'd be running is I get the compiler, I specify the name of my output file, and then I give it the name of my my C file. I can just do that. Typo. And then I can just run it here, right? Yeah, so that's integers. And now we also have floating point. So integers are fine, but what if you want to represent something that's not an integer, so like a fraction, we want to have a decimal point, so on. I think at least those of y'all who are doublies have probably covered this in 306 at least, but it's the same idea where you have numbers that are not integers. But we can also have different kinds of floating point values. So we have float, which is a 32-bit floating point, and we have double, which is 64-bit floating point. One thing to note though is that floating point numbers are imprecise. So some numbers can be represented perfectly by floating point, some cannot, and you'll get like an approximation, which means that there basically there's some rounding that goes on whenever you do floating point math, or even sometimes when you just declare a floating point number. So some things like comparing them for equality sometimes doesn't work, and we'll see an example of that. This also requires hardware support to be efficient. So in your computer, you have some hardware that's meant for doing integer math, and you'll have some hardware that's meant for doing floating point math. On your, let's say your laptop, this is not something you need to think about a lot, but on Solar, when we're writing for an embedded system, it actually, to turn on the floating point unit, uses some extra power. And in the operating system we're using for BPS and controls, there's a bug, so the operating system doesn't handle the floating point hardware properly. So if you use the floating point hardware, it will crash the system. So you can still use floating point, but you have to emulate it in software, which is very slow. So we try to avoid it. Yeah. Any questions so far? All right, let's go see my example. So yeah, this one's a little bit shorter, but I can declare, again, I put the type first, then I can declare my variable, and I can give it a value. So in this case, we have 0.1 is the value I'm giving it, and then I can specify f if I want to make it to make this thing here single precision. I don't have to specify it because in this case, the C compiler is smart enough to convert it when it sees that I have a float here. But by default, if you just write like 0.1, by default, it's going to be a double. And sometimes you don't want that because, again, on the systems we use for Solar, even if you have the floating point hardware working, a lot of the times in an embedded system, you'll only have the 32-bit floating point hardware available. So if you have a double, it's going to be very, very slow to do that computation. Whereas if you have a float or like single precision, you can get hardware support, or even to do it in software is going to be a little bit less expensive. Yeah, so we have doubles and floats. And then, yeah, we can assign them. we can do division with them. So what this divided by equals here is saying, this is equivalent to saying bar equals bar divided by 1,000, and it's just a shorthand. And then we can, so yeah, let me just run this program. I think it's an interesting illustration. So got this code here. And if I run it, I get bar, I print out bar, right? So I get 0.1, some trailing zeros. And then, well, I print out foo and then I print out bar. They're both 1 with some trailing zeros, right? So simple enough. But then now I say if foo is not equal to bar, I want to print out that they're not equal, right? So I'll print out foo and I'll print out bar with this not equal sign. And whoa, they're not equal. Right. So what's going on there? So if we look at this, my VS Code is smart enough to tell me that I don't actually have 0.1. I have 0.1, bunch of zeros, 1, 5, because floating point can't perfectly represent 0.1. And then if I look at, okay, here, it's not going to show me, but basically you're going to end up with something that's almost 0.1 and almost 0.1, but not quite the same. So when you check for equality, it's going to compare every single bit. So if any tiny piece is wrong, it's going to say they're not equal. And here foo is a float and bar is a double, but even if I have baz, where are they? Okay, I'm comparing a double to a float both times, but they're both not equal. So when you do comparisons with floating point, if you want to check for equality, a lot of the time you're better off checking, is it close enough instead of is it exactly equal? Because to get it exactly equal requires a bit of luck as well. So yeah, questions about this? All right. Between like float and double? Yeah, you can. It's just whenever you convert from a double to a float, you're going to lose some precision. And then if you convert from a float to a double, it's just going to pad the rest. Okay. So we've also got pointers. So this is maybe where we start to get to the point where some of y'all who have had maybe like Python or Java before, we're going to start seeing some new stuff. If you've done C before, maybe these are familiar. So with pointers, the general idea is you can keep track of the location in memory of a thing. So it could be an integer, it could be a float, it could be a user-defined type, it can be an array. So the way that C implements arrays is as pointers. So you'll have a bunch of things that are continuous in memory, and the pointer will point to the start of it. So you can have, for those of you who don't know what an array is, it's like a big list of things in memory. So in C, you just keep track of the start of it, and then that's how you have your array. And then you also need to sort of you need to keep track of how long it is as well if you want to know that. So got an example here. So here, I can declare some variables up here. So I've got a couple of integers that I've initialized, and I've also got an array. So if I want to declare an array, I can say the type of the individual item in the array, and I give it the name, and I get these curly braces, or not curly braces, I get these square brackets with the number that is how long it is. This number isn't mandatory if I specify all of the values here, but I can put it there. And then I have these curly braces and I can list out everything in my array. So like baz 0, so arrays are 0 index, so like baz 0 would be 0, baz 1 would be 10, and so on. Yeah, so there's also some different operations I can do with pointers. So if I have foo here, this is an integer. I can also declare a as a pointer to an integer. So this little asterisk here means that a is the pointer and its type here is integer. And then this little this ampersand here says take the address or take the reference of this variable. So I can say a is equal to the address of foo, and I can make another pointer called b and set it to a. So now a and b are both going to be pointing to foo. And then yeah, I can still print out foo. And let me run this code actually. So I've got my code here. And if I run this, I can see, yeah, foo starts out as 0, which is what we would expect, right? And then what am I doing here? I'm saying, look at A, and then this asterisk here, it can also mean if you do it to a pointer and you put an asterisk in front, it says, get me what this pointer is referring to. So in this case, A is referring to foo, and I can set it equal to 42. Okay, so now whenever I print out foo, I get 42. And then I can also say, let me print out, what does B refer to? Right. B is gonna refer to 42, and that's because back here we said B is gonna refer to A, and A refers to foo. So B refers to foo, and we've just changed foo through this. So now B is also gonna refer to 42. Does that make sense? Okay. Yeah, so I can do this again. I can change A. I can change that value referred to by A to 7, and now I can say A refers to bar instead of foo. So now foo is 7 because I changed this here. Sorry. This here will change foo to be 7. So we set here. And then now A refers to bar. So if I say I print foo, and now if I say what does A refer to? Now we get 19. Right? I can also now I can say A is equal to baz. So for those of you who don't remember, baz is this array up here. Notice how I don't need the asterisk here, because when you have an array, you're allowed to treat it like a pointer without needing to do this this reference thing here. So now when I do this, A is going to be pointing to the start of baz. And what I want to show here is we can also do math with pointers. This is generally something you should try and avoid, but sometimes you don't have a good way around it. But if we look here at what we're doing, I'm saying add 2 to A and then dereference it, okay? So what that's going to do is, so A is a type, it's an integer pointer. So whenever I add 2 to it, it's going to go 2 integers forward. So A was pointing here to the 0, but now I add 2, so I go 1, 2. Now I'm pointing here, so I get 20. And then here I've got something that looks very similar. I have star A plus 2, but notice there's no parentheses anymore. So what's going to happen here is I'm going to dereference A, which points to 0. It points to the start of Baz. And then I'm just going to do a normal add 2 to it. So 0 plus 2 is going to be 2, as we might expect. So that's what we see here. And then the more clean way to do this, which is generally recommended, is I can also use curly braces to index into it. So if I say a curly brace to, or not curly brace, square bracket to close square bracket, what I'm saying is get me the thing in the array A that has index 2. So that's also going to be 20, right? Because it's 0, 1, 2. So any questions about this? Yeah. Yeah, that's a great question. Yeah, so whenever you use it in the declaration, you're saying treat this like a pointer. So so you're saying I'm declaring a pointer here. Whenever you use it anywhere else, it's saying the compiler already knows that it's a pointer. And you're saying, I know this is a pointer. I want to find out what it points to. So, so in this case, you're saying in the declaration, yeah, you declare it as a pointer, and then you say, now I know this is a pointer. I want to treat it as an integer now. Like I want to see what it points to and get that value. Yeah, no problem. Yeah, there's also some other stuff with pointers, but I don't want to get too involved today. Yeah, so the next is we can also have types that are defined by you, the programmer. So there's several motivations we want to do this. One is maybe we want to group multiple types together. So we can group them together in 2 ways. We can have a structure which says we have multiple fields in this type, and we can assign things to each one of these fields, and then they're like packaged together in one like object. And then we can also have unions, which are a similar idea, where you have several different fields that are packaged together, except only one field in the union can be set at a time because it uses up the same location in memory. We've also got enums, which are basically if we have a group of integers that we're using together, we can assign them all unique names that make it easier to refer to them. And then just to give us even more flexibility, we have a thing called typedef. Oh, I was double clicking and then I realized that's probably not what I want to do. We have a typedef, which is used so that you can define more type names. So I've got another example here. Yeah, so here, first what I can do is, let's say I have the floating point type that we saw earlier. And let's say I want to give it a new name. What I can do is I can just say typedef and the name of this type, and then I give it my name. So now if I say my float 32 underscore t, this is actually referring to a float. I can also declare a union. So here, so in this example, I made students, right? So a student can have a grade, and let's say it can be an integer, can also be a percentage, which is going to use. So for an integer, we can make that unsigned 32-bit integer arbitrarily. I can also make the percentage a floating point value. And let's say I also wanted to be able to access the raw bytes of their grade. I can also have an array of unsigned integers. So this is just giving me 3 ways to access the same data. I can also have an enum here. So let's say I want to keep track of if the student is like a freshman, sophomore, junior, senior. I can just declare an enum called year, and I can even type define it to be year_t. And now I can use this. So let me show you in the actual code. So what's actually going on here, if I hover over it, it's going to say, whenever I put freshman, it's actually just going to mean 0. And whenever I put sophomore, it's just going to mean 1. And then we get junior and senior. So the reason this is useful is whenever you declare them in an enum, it's going to guarantee, like the compiler will guarantee to you that they're all going to be unique values. So if you need to have different things like this where they need to be unique, and you don't want to, each time you add something, you don't want to go have to maybe change all the values, you can just use an enum and the compiler will take care of it for you. Yeah. You do not. Yeah, so if I didn't have this type def here, I couldn't call it year_t, but I could just refer to it by saying enum year. Yeah, it's a good question. Yeah, so the difference between union and struct is if I have a union, if I set let me run this code. So if I have a union, which is in this case, student.grade is going to be a union. So if I declare a student here and I set his grade percentage to be 95, okay, I can access as an integer or as a percent, and as the percent it's going to be correct, but as the integer, it's going to give me this. And what this is actually going to be is this isn't our random value anymore. This is actually okay, so theoretically you could get a random value. This is like not necessarily good practice, what I'm showing here, where you like reference the field you haven't set yet. But actually, let me show you more specifically. So if I set it to 0 here, and then I recompile. So even though I set integer to 0 here, I still get the same value we have here. And the reason for that is integer and percent and bytes as well. These all share the same location in memory. So this is going to be 32 bits of memory. This is going to be 32 bits of memory. And this is going to be 32 bits of memory. But they all have the same 32 bits. So if I set one of them, the other values are not going to retain their original value. Whereas for a struct, if I can set the year, the grade, and the name, and I have space to set each one of those all at the same time. Yeah, so yeah, so for a struct, I can put other types inside of it. I could also put, so I can put my own types inside of unions. I can also put my own types inside of structs. So yeah, I can have a student with his year, his grade, and his name. So what I've done here is, if I want to set a field in a struct, I can use this this dot operator here. It says get me that field, and then it's the same syntax here for a union. I can say, so John.grade is the union, and then dot integer says I want to set this field. And then I can set his name, I can set his year, and then I can use this thing called so I print out this. We've already seen his grades. But I also have this thing called a switch statement that can be useful, particularly when you have like enums. So what this does is I can say switch, and then I pass in a value. And this needs to be like, it needs to be like an integer or a float. So you wouldn't want to pass like a string to a switch statement in C, because you're just going to be passing a pointer. You're not going to pass the whole string. But what I can do is it's going to look at John.year, and then I can sort of have like a lookup table basically of different. If John.year is freshman, I go to this case. If John.year is sophomore, I go to this case. And if it's junior, I go to this case. Senior, I go to this case. So what'll happen is I'll go to the case, and I'll just start executing code, and until I see a break statement. So in this example, we print out welcome because I've set his grade to his year to a freshman, and then we break so we don't execute any of this code. I can also have a default. So if I don't specify all of my cases and I get something else here, I can execute the default. Yeah, and then I have a print down here to look at his name. But like if I change this to, let's say, junior, and I recompile, so now I see old, even though old is under senior. And the reason for this is junior doesn't have a break after it, so it's just going to keep executing, and it's also going to execute senior's case. Yeah, so any questions about this? All right. Yeah, also I haven't really been talking about the printfs very much. I just kind of said you print stuff, but sort of the format for that is you pass in a string, and then you have these things called format specifiers where you put like a percent and then a letter. There's a bunch of them, you can look them up, but D is for decimal. So whenever I've been printing integers, I've been printing them in decimal. So that's what's going on here. F is for float. So since this is a float, I'm putting it in floating point form, which gives me this. And then I can do %s is for a string. So since John.name is a character array, I can do that here, and this will work. Yeah. So what next? So types are nice and all, but we also want to be able to do operations on them, and C gives us a lot of different operations. So we have like our assignment operation, which we've already seen, where you can have one type or some constant or variable or constant, you can set it, assign it to another variable or to a constant when you're initializing it. We also have arithmetic, so plus, minus, multiply, divide, remainder. These are all things in C. And then we also have logical operations. So for those of you who are taking 306, you might know about like and, not, or, XOR. We have all of these in C, and we have a Boolean version and a bitwise version, which I can get to in a bit more detail. And then we have reference and dereference, which you can use on pointers, which we've already seen. So this example, Oh, we've also got Booleans, which I left out, but a Boolean is just going to be true or false. So yeah, I'm realizing I also forgot. There's more operations. This is not like an exhaustive list. Um, for example, I'm realizing now I forgot the equals and the not equals operation, which will tell you if two things are equivalent or if they're not equivalent. But here, just some examples. We have like assignment, addition. So plus, hopefully A equals B plus C. This does kind of what it looks like. You add these up and you assign them to A. And then we can also do something called plus equals. So what this is doing is we take this, we put it in front of the equals to get this operator. And what it'll do is it'll say A equals A plus 4. So turns out it's relatively frequent. Then you'll be writing some code and you want to do an operation where one of your source operands is going to be the same as your destination where you want to store it. So the shorthand is used for most of the operations can do this. We also have the plus plus operator, which can go either after or before your variable. And what this is going to do is it's just going to add 1 to your variable. So this is also something that's fairly common. The difference between doing it after and before is that it turns out whenever you do these operations, they're going to return something. So what you could do is you could say like B equals A plus plus or B equals plus plus A. The only difference is A plus plus is going to return A. It's going to return A, like pass it to the left, and then it's going to increment after, so it's a post increment. Plus plus A is going to increment before and then return the value. One thing I'll note if this is like confusing is it's generally agreed upon that this is kind of confusing. So usually you wouldn't write code. You try to avoid writing code that relies on this behavior, but sometimes it makes sense. Like if you're putting this inside of like the index for an array, maybe if you're looping through the array, sometimes you might see this, but one thing that is kind of a no-no would just be to like arbitrarily mix like this one and this one, because then someone has to look and see, oh, are you actually trying to differentiate here? Or are you just like having fun with your operations? But just know that both of these exist. Yeah, we've also got subtraction, so it's sort of a similar syntax to addition. We also have the minus minus, and can do it here as well. So the same idea as plus plus, except this is subtracting 1 instead of adding 1. We also can have negation. So if we put a minus in front of something, we can just make it negative. Also got multiplication, division, and modulo, which takes the remainder. We can also do like times equals, divided by equals, modulo equals. I just didn't write them all out. Yeah, so this is arithmetic. We've also got logical operations. So I can have Booleans, which are like true or false. And I can do like and, I can do or, and I can do not. So this is the syntax for that. And then the way that a Boolean is going to be represented sort of under the hood is it's going to just be an integer. And if it's all zeros, it's false. And if it's not all zeros, it's ones. And then if you have true, usually this will just be a 1. So like all zeros and then a 1 at the end. But a lot of the times you're not going to rely on the exact representation of like true, but just something to be aware of. We also have bitwise operations. So this operates on like the whole value, whereas what bitwise will do is it will look at it'll do the logical operations on individual bits in your variable. So if I did foo and bar bitwise here, this one here is going to evaluate to 0 because this bit here is going to line up with a 0 over here, and the one bit that sets the 4 is going to line up with a 0 over here. So I'm going to get all zeros. Whereas if I had done, like, let's say a logical AND, both of these are going to evaluate to true. So I would have gotten true. So yeah, we've also got bitwise OR, we have exclusive OR, and we have bitwise not. Yeah. Any questions so far? Yeah.
Well, it looks like bitwise and not is the same syntax as arithmetic negation.
Oh, it's actually not. So if you zoom in a lot, this is a minus sign here. And this, the bitwise not, this is a tilde, but it does look very similar. So yeah, it's yeah. So I guess try to not put like, so hopefully like the goal would be that if you're writing code and you want to be able to tell them apart, usually if you're doing something with negation, you'll be treating them as like numbers, whereas if you're doing something with bitwise not, you'd be treating them as like bit masks, or like bitmaps. So like, I guess don't abuse like the not where you'd expect negation and negation where you might expect a not, because it doesn't really make sense to mix them, but like if you did, you could make some pretty difficult to read code, right? So that's a good point. Yeah, anything else? All right, we've also got pointer operations that we've already seen. So we have reference, and we have dereference, and we have index. So yeah, this is just to take like the address of something. This is to do the opposite of that. So like look at that address and see what you have there. And then this is for indexing into an array. So any questions about this? All right. So next, so now that we know how to define types, we know how to manipulate them, but maybe we want to have a program that has some control flow. So maybe do something, but only in certain scenarios, right? So there's a few ways that C provides that we can do this. So one is we can have if statements, which is, we can say if, and then we can test a Boolean or a condition, and then it can do that or not do that. We've also got while loops, which will keep doing the same thing until a certain condition is no longer met. And then we have a for loop, which is sort of like a shorthand for a specific case of a while loop where basically you set something up, you have some initial setup, and you have your condition you're testing for, and then you have something you do at the very end of the loop. So an example might be if you have an array and you're going through it, maybe you start at the beginning, and then each time you go through the loop, you go to the next value until you get to the end. We can also have functions. And what this does here is sometimes you want to break your code up into different logical pieces just to make it easier to organize. Okay, there's some other reasons as well, but mainly to make it easier to organize. And then Yeah, so we can look at our example. All right, so here I've got a bit more complicated file this time. So we still can have our variable declarations. Can also still have them declared locally, I mean globally. And still have our printfs, right? But what we can do is, let's say I want to know if two strings equal each other, and the way I'm going to define this is every character in the string is equal to like the corresponding character in the other string. And let's say I might want to do this a lot of times, so I don't want to rewrite the same code over and over again. So I can write what's called a function, where it will return some value. Here I've chosen integer. I thought I had changed this to bool, but I guess I did not. But it's not a big deal. So a boolean is just a special case of an integer in C. So what I've got here is I can say the return type. So a function can return a value. It can also return void, which means it has no return type. And then I can give it a name, and I can give it parameters. So I have a comma separated list of parameters I can pass to my function. And the format for this is I have the type of the parameter. So in this case, pointer to a character, which is also a string. And then I have the name. Okay, and then I have another pointer to a character that I called S2. So I want to see if two strings are equal. So I want to see if S1 or S2 are equal. So what I can do is I can declare some variable here, I, set it to 0. And I can use this to keep track of what my place is in the string. So I start at position 0 in the string. And I'm just going to assume that the strings are not equal for now. So I'm going to set my result to false, and result is just a name. I could have called this whatever I want. And this is going to be a Boolean. And now I can have a while loop. So I can say, as long as S1I and S2I, so as long as at the place I'm at in these strings, as long as they're equal, I can keep going, because my string is still equal. I haven't shown yet that they're false. And as I do this, I can increment I. So I go to the next place in the string, so that whenever I loop back, I can test again. I can also check and see if we're at the end. So in C, the convention for a string is you'll have your array of characters, but then you'll have one additional character at the end, which is the null character, which is just 0. And I can also specify, I can notate the null character as like a \0 as well. So it's just a different way of writing it. So if I reach the end in string 1 and I reach the end in string 2, that means that I've been able to loop through the whole string and they were equal every time. So I can set my result to true. And then I can call this break statement. And what this does is it breaks out of the loop. So the reason I might want to break out of the loop is once I don't want to go past the end of the string and keep checking, right? Because this would just be a garbage value. Yeah, and then I can return my results. So I'll either find some index where they're not equivalent, or I'll find they're all equivalent and I'll return my result. And then I can do the same thing. So let's say I have another array and I want to find the maximum value. But let's say I don't want to have this int I here, and I don't want to have this. I want a shorthand. So what I can do is C gives me that shorthand. It says I can have a for loop. And at the very beginning, I can declare a variable called I and set it to 1. And I can make this test that I is less than the length of my array. So you want to make sure you don't go past the end. And then I at the end of my loop, I can increment I. So what am I doing here? I'm guessing that maybe the max of the array is going to be the first element. So I initialize it to that. And then I check every element in my array. And if my maximum is less than the thing I'm on right now, I can update it and I can return the maximum. Okay. So this is another function I've defined. And what I can do is I can go down here and call these functions to get a value. So let me show you this in the actual code. Yeah, so I've got the same thing here. And if I run this, I can see when I find the max in this array, I get 7. And then when I check string equals, if I see if hello1, which just says hello, and hello2, which also says hello, I can see they're equal. So I get a true, which is also a 1. And then whenever I check if hello equals letters, which I can also declare a string like this, just the same way I declare an array. These are not equal, right? So I have HEL and then it ends. So I get false. So any questions about this? It will probably let you do that. So if we look at Boolean, what it actually is you have this like header file that will define it, like loops through a bunch of stuff. But it yeah, so what it's doing here is you can have something where it literally just says define true to be 1 and define false to be 0. But the actual should be able to just say yeah, so it'll accept this, right? It's just maybe you don't want to do this in your code just because it's going to be harder to read. Yeah. Any other questions? The thing I showed just now?
Yeah.
Yes, that's inside std_bool.h. So this is C provides some standard libraries you can use that will define things like bool and some of the like the uint8 is defined in like a different header file, or like printf is defined in stdio.h. So printf is just a function that is defined somewhere. Yeah, so it's just defined in one of the library files.
Well, like, what does that define?
Oh, it's a good question. That's the last example I have. I'll go over that. But you can think of it as just saying, whenever I see this, it's like a sort of like a find and replace command to the compiler. So yeah, any other questions? Okay. So yeah, okay. We're actually almost there. So this is fine and all, but sometimes you'll have a more complicated project than just like the example test cases I've shown you so far. So whenever we have a big project, we can divide it up into source files and header files. And the convention is the source files will get the extension .c. And then the header files will get the extension .h. So C for C programming language, and then H for header. And then we can also, whenever you declare, whenever you have like a variable or a function, there's actually a distinction between defining it and declaring it. And it can get a bit pedantic, but especially for functions, it's something you should at least have like a passing understanding of to help you navigate like a more complex code base. We also have macros and the preprocessor. So in addition to the compiling the code, there's a thing called the preprocessor, which is like the first thing that runs in the compiler. And it goes and does like a bunch of cut and paste stuff to your code if you tell it to. And then whenever we compile our code, as you get more and more files, or even if you just don't want to keep typing the same compile command over and over again, you can have a file that manages those rules for you called a makefile. So we'll look into how that works as well. Yeah, so I have one of my example programs here. So in the past, all of my includes have had these little like chevrons around them. And what the chevrons mean is that this is like you have like a standard include path. So that's where all your like standard libraries are going to be. So if I have a standard library and I want to include it, I have it inside of like these chevrons, or like the less than greater than sign. But if I write my own header file, I can put quotes around it, like here in header.h. And what the quotes do is they say, first look in the directory I'm already in, and then I can go look at my standard include path. So this is going to give precedence to the one that you write. So I could write my own file called stdio.h and put it in this directory and then include it with the quotes. But yeah, so hash include is it lets us use functions and variables and other stuff from outside of this file. And the way it does that is it basically just does a copy paste, and it copy pastes header.h into this file before it gets compiled. So let me show you this. So can include header.h, and if I look at header.h, I can put some stuff in it. So this looks probably a little bit more confusing than some of the other files I've shown you, but what's going on here is, let's say I copy paste this file in, but let's say maybe I have a lot of files that are including header.h. I don't want to copy paste this in the same time, or I don't want to copy paste it over and over and over again. And the reason for that is if I have like a function or something and I declare it a bunch of times, the compiler is going to get confused and say, hey, you declared this like 5 times. What are you doing, right? You can only declare it once. So what we do is we'll say, if we have this symbol called header_h is defined, or if it's not defined, we can paste in all of this stuff. But right after we start pasting it in, we're going to define this symbol, so that next time when we include this file, it's going to say, is header_h defined? And it is, because it's been included before. So we're not going to paste this in. So this is just something you need to do whenever you write your header files. You need to make sure you have these header guards. Otherwise, you can get some really weird errors. I can also use hash define for other things. So if I want, I can also say hash define foo or like some name to something else. And what this will do is now whenever I write foo in my program, what the preprocessor will do is it's going to just take foo out and it's going to paste 42 in. So I can use this kind of like a variable or a constant, but not quite, right? This is one of those cases where it now all of a sudden it makes sense why you might want to put something like u or some other type specifier after it, because foo doesn't have a type. It's just copy pasting in 42. So maybe if you're putting it somewhere that you want it to have a specific size, maybe you can use for a specific signedness, you can specify that here. We can also have macros that act like functions. So whenever someone says a macro in C, they mean hash define. So I can define a macro called min, and it looks kind of like a function. I have my parameters, but they don't have types. Okay. So what this will do is if I write min and then I put something here and then a comma and then something here and then a comma and then close the parentheses, it's going to just paste this in, and it's going to replace whatever I put for A with A and whatever I put for B, B. I've also introduced another operator here that I didn't show earlier, but actually a few that I didn't show earlier, but just sort of to unpack what's going on here, I am saying we have this question mark operator, and what it does is it tests whatever it has to the left as a Boolean, and then if it's true, it will return the thing right after it. If not, it's going to go after this colon and return this. So it's going to say, this is sort of equivalent to saying if A is less than B, give me A. If not, give me B. So this is just going to take like the minimum of A and B. And then here we have this less than operator. It does what you might expect. It lets you know if the thing on the left is less than the thing on the right. Note I also have these parentheses around A and also around B. The reason for this is that if I was going to pass something to, so every operator in C has like an order of precedence. And let's say I passed, say I called it like min 2 or 4 and 7, something like this, then this bitwise OR has a lower operator precedence than less than. So, but whenever I call a function like this, what my intention probably is that I'm going to do the bitwise OR, and then I'm going to do the comparison. So, yeah, we put these parentheses here just because when we're doing copy paste, we need to worry about operator precedence. So these parentheses will force the precedence to evaluate to what you would expect instead of like maybe giving you some weird errors. So questions about this? All right. Oh yeah.
So why would you not put the A less than B in front? You just want it.
Oh, that's a great question. So if I had let me put this back. So if I have this, what this is actually going to evaluate to is I'm going to do the copy paste, and let's say I had so you're saying if I did something like this.
Yeah.
Yeah, so what we're going to do is A is going to be this, and then B is going to be this, but it's literally just a copy paste. So what I'm going to get is I'll get 4 or 2 less than 7. And then I will get 4 or 2, 7. And then, so now if we want to evaluate this, we need to do this first. But the way this evaluates is you could evaluate this, which would evaluate to 1, right? So you're going to end up getting 4 or 1, which will give you like 5. So in this case, it would still work, but if I had you could come up with a case, right, where this would break it. All right. Yeah, but that's a good question. This is like a very commonly missed thing. All right. Anything else? All right. Yeah, I can also, let's say I have a variable called hello1 and it's in this file. So I've given you, let's say I have another file called lib and I have a variable in here and I have a function in here and I want to use this in another file called source. What I can do is if I want to use this variable and this function, I can, this is a variable definition. This is a function definition. They can also work as a declaration, but a definition is like a subset of a declaration. So what I can do is if I want to use this code in source, one option would be I can just, I can just copy paste this over, right? But maybe maybe I want to use this in like 100 different files and I don't want to copy paste it 100 different times. What I can do is I can just say, if I have this function called string equals, and if you want to call it, it looks like this. And if I just copy paste this into my 100 files, the C compiler is going to know based on this function signature how it needs to generate code to call this function. And then later we can, the C compiler, the linker can then link all these files together so that they can all call the same version of the function instead of needing to copy paste it everywhere. We can also do the same thing for a variable. So it'll say, there's a variable and it exists and it has a type character and it's an array. Yeah, so what we're essentially doing here is we're saying I have this function and it exists somewhere, and I have this variable and it exists somewhere, and later I will tell the compiler later in the compilation steps, we'll tell it where to find it, but for now we can just tell it this is what it looks like. So what that means is in source, I can call this function, and even though I haven't declared it, all it has is a copy paste of just this. Yeah, I can also just sort of to illustrate, yeah, so I can call my macro. And one of the nice things about having your function macro as a macro instead of a real function is I can have one and I can pass an integer to it, or I can pass a float. And it's okay with it because it's just doing a copy paste. It's not doing any type checking. I can also abuse hash include. Don't do this in like your actual code. This is just like a demonstration, but I can include stuff.h 3 different times. And what I've actually done in stuff.h is I can say, if I haven't defined this, define it, and then we're just going to paste this in, right? So this isn't part of a function. This is just like floating statement. And then if not, so this is already defined, I can define by, and then I can just paste this in. So what I can actually do is if I look at my source file. I pasted in 3 times. So what do we think is going to happen the first time I have hash include stuff.h? Maybe I can split screen. So what am I gonna paste in here? Does anyone want to take a guess? Yeah, so I'll paste in hello world, and then what about this time? Yeah, so this will paste in bind. What about the third time? Yeah, nothing. So let's see if we're right. So run. Yeah, it prints 1 because hello 1 does equal hello. And then it prints hello world with the exclamation marks. And that's here. And then it prints vi. And then it's done including now that like the third time we paste it in, it's just nothing. So yeah. Any questions about this? Okay, and then the thing I've been using to compile this whole time is what we call a makefile. Go back to. So what I can do here is instead of having to type out like GCC-O, the name of my program, and then like the file name, what I can do is I can just put a rule here called floats. And if I say make floats, okay, if I delete that, then you can see it just runs this command. I can also add, let's say I want to add the same flags to every single command I have here. I could just have a variable, set it, makefile variable, set it equal to -g, and then every time here I have this like $sign, C flags, it's just going to paste in whatever I have like here. So that's where I get this -g, and -g just adds debugging symbols. I wasn't sure if I was going to run any of this code in the debugger or not today. Yeah, so one thing that's nice is if I try and run make again, it'll actually tell me, oh, you don't need to compile, you're up to date. And the way it knows that is I define this rule and I say it depends as a dependency on this file. So if floats.c changes, it knows that it needs to recompile floats, but if not, it can say, oh no, we don't need to do this. You're all good. So this can save you some time if you have like a big project with a lot of files that need to compile, if you don't need to recompile all of them every time. You can also set the first rule is just what it runs by default if you just run make. So what I've done here is I have a rule that just depends on all of the different programs I run. So whenever I change any of my example programs and I type make, it's only going to build the ones I updated, right? So you might have noticed earlier, I typed make here after I made some changes and I compiled user types. Here I typed make and I recompiled program flow and so on. So it doesn't need to recompile them if you haven't changed them. Yeah, also if you want to build a program that has multiple files in it, so the example is called source. What you do is you can make it depend, you can compile each source file separately. And the way you do that is you would specify the name, you'd make a rule for the individual file you want to compile to an object file. So let's say source.o depends on source.c. And if I want to compile source.o, I can use my compiler, and then -c says just compile, don't link. So it'll just do that one file and it'll skip the linking step. And I compile source.c, so this will create source.o. I did the same thing for lib.o. And then whenever I want to actually link those different object files together, I can take the compiler. I tell it I want my output file to be called source, and I just list the object files I want it to link, and it'll just do it for me. So this is maybe a lot, but any questions about this? Yeah, so I'm linking these files because whenever I compile source.c into source.o or lib.c into lib.o. So if we look at these files, source.c just does this, but it calls this function, which is declared in lib.c. So in order to use this function, it's declared in a different file, or defined in another file. I need to compile this function and produce like object code that will implement this function. And then I also need to compile this file and get some object code that'll implement main. But then I have two pieces of object code that need to be combined into one piece of object code. So that's what the linking step does. So what it'll do is I have this installed. So if I look at, I can actually, you probably won't need to do this in your so you probably aren't going to need to do this when you're on Solar, but just if you're interested about what's really going on, is you can actually look at the object code it generates. So if I look at lib.o, it's going to create this function called string equals and like generates a bunch of machine code that implements it, right? And then it'll also have some other stuff for like, yeah, so it has like the hello1 variable is here, and it's got some other stuff as well. And then if we look at source, we have our implementation of main, and where is it? So which file am I looking at? Yeah, so what it's going to do is it's going to have these like function call instructions that it uses to call functions. And it's going to mark like, so you see this nasty looking x86-64 thing here. This is whenever the compiler generated this object file, it said, okay, in the header file, you told me there's some other things that exist that I'm going to be given at link time, but I don't know how to finish generating the object code yet. So I'm going to put this guy here to say whenever I go to generate the object code, or whenever I link, I need to update these values to like the correct one based on the object code I'm given from your other file. So if we look here, we've got this one here is for like string equals. So it's waiting on whenever we link, we're expecting to be given a function called string equals. So if we're not given a function called string equals, we'll get an error at link time. But if we are, then it'll go in here and it'll update the object file to get rid of this guy. And then we can also see this for like hello1, which is that global variable we declared in another file. And then we can see that our friend printf is also implemented like this. So at link time, it's going to get it's going to link to the standard library where it's defined printf. So any other questions? All right, so that's all I've got for today. Yeah, so any like final questions about C? All right, I think we can probably stop recording. Rishi, are you there? My volume on. Okay.